common medium for waves to propagate through is a string. Well, a good example of that would be a guitar. Waves are propagating along a string in this instrument. And we can calculate the speed of waves in a string if we know the tension of the string and we know the mass density of that string. So in general, for waves, the speed of a propagating wave is the wavelength, lambda, divided by the period of one oscillation. This kind of looks like distance over time. Speed is distance over time. Distance, the length of the wave, divided by time that it takes to do one wave cycle. That's generally true of all waves. For waves on a string, we also have a relationship that this wave speed equals the square root of the tension in the string divided by this quantity mu, the mass density. So now we're using our Greek letter mu for another purpose. In the past we've used it for friction. Now we're using it for linear mass density. So mu equals the mass of the string divided by its length. So what this equation is saying is that the more tension there is on the string, the faster a wave will move through it. And it's also saying that the more mass the string has, the slower the wave will move. So let's do a little example. This is example 13, 10. And we've got a setup with a string attached to a wall that then goes over a pulley and is attached to a hanging mass. So there's hanging mass little m, and we're given some information. String mass, capital M, is 0.03 kilograms. The string length is 6 meters. And the hanging mass is 2 kilograms. So let's figure out how fast waves would travel in the string. Like say you pluck the string and it creates a little wave, then moves along that string. What's its speed going to be? Well, the first thing we need to do is figure out the tension in the string. And we can do that by looking at a free body diagram for that hanging mass. Hanging mass has gravity pulling down. It's got the tension from the string pulling up. It's stationary. So it has zero acceleration. tension minus the weight of that thing equals 0, so the tension force equals mg. What else? Oh, we need to calculate this mass density mu. Mu equals capital M, the mass of the string, divided by its length. And now that we have these two things, we can plug them in to our equation. T over mu. I haven't been plugging in numbers, but the final value here that you'll get is 62.6 meters per second. All right, so that's one application for calculating speed of waves on the string.